The broadcast is now starting. All attendees are in listen-only mode.
Good morning, everyone, and welcome to our webinar today on Leakage Current Testing 101. I do apologize for some audio connections issues that we're having at this point, but we're going to go ahead and start with our webinar today. The topic is Leakage Current Testing 101, and so as usual, let's take a look at our team.
Hi everyone, this is Amanda. I just want to let you know that we're having some connection issues, so we're going to fix that and then we'll be right back.
Okay, everyone. Once again, we do apologize for the issues that we're having with our audio today, and we're gonna try this all over again. I'm gonna shut down the video so that to make sure that we don't experience any audio issues anymore, and hopefully we won't. But once again, welcome to our webinar today on Leakage Current Testing 101, and I'm your host, Syed Abidi, actually the presenter, one of the applications engineer. And Bishan Patel is helping us today as a panelist. He's also one of our apps engineers, and he'll be helping you guys with any questions on the chat line. And then we have Amanda Booth, who's basically running the show, the organizer. And if you have any questions on the material being presented, audio, video, or audio connections for today's webinar, you can reach out to her via the chat line. Same notes that I pretty much just repeated. Q&A facility, we always have one on the chat line, so feel free to utilize that. And again, Bishan will be happy to assist you with any questions on the material that's being presented. A recording of this webinar and the presentation will be available on our webinar archive page on this web address that you see on the screen. And once again, if you have any other questions on anything else regarding the webinar, feel free to email Amanda or reach out to her on the chat line. It's also Halloween day today, so happy Halloween to all those who are celebrating. So let's, with that said, let's dive into the material and see what we're trying to cover today. We're going to start with understanding what is leakage current. I know we've talked or used this term leakage current in some of our previous webinars when it comes to HiPod testing. So we're going to make, we're going to make sure we understand what leakage current are we talking about this time around. We're going to look at, how is it measured, how is it performed, and what are the requirements from the standard. We're going to look at two different types of leakage current today, earth leakage and touch current, or enclosure leakage as it was formerly known as. And again, we're going to look at how it's being measured. I have a little video demonstration for you guys to go through some of the basic parameters when you're setting up a leakage current test, and some examples from the standards. Okay, so before we start learning the leakage current test, it's always a good reminder to look at this chart that I've been trying to update, and since it's Halloween day today, I tried to look for some volunteers so that I can update some of these readings, but I couldn't find any. So what's important to look here is the readings from 6 milliamps and up. That's the danger zone. That's where the danger zone starts, which means that any current from 6 milliamps and above can result into severe injury and possible death. So keeping these numbers in mind, we're going to look at some of the maximum allowable leakage current values from the standards and see how, see if we can make some sense out of those readings. So going back to the HiPod test, I know we've mentioned the term leakage current a few times in the past, especially when we were talking about the HiPod test, because it's one of the main measurements that's being made when insulation is stressed using high voltage. And so that's leakage current for the HiPod test, which results when the insulation is stressed by high voltage, and it allows some leakage current to flow. Whereas the leakage current that we're going to talk about today is different in the sense that it's, first of all, the device under test is, or it needs to be powered on. So the big difference between the leakage current being measured during a leakage current test versus a HiPod test is that during a HiPod test, you're just stressing the insulation with the high voltage and the device is not powered on, or the circuit is not energized. Whereas during a leakage current test, you have to power on the device under test and make some leakage current measurements by simulating a number of different fault conditions and also utilizing a measuring device circuit. So the two different types of leakage current tests that we're going to take a look at today are the protective conductor current, also called the earth leakage current. It's basically the overall leakage current which flows in a protective conductor, which is the main protective earth conductor of the device. And I'll show you a little picture to better understand what this leakage current really means here. Earth leakage current means here. And then the second one would be that we're gonna look at today is the touch current. It was also formerly known as enclosure leakage per some test standards. And this leakage current is basically the current that can flow through a human body when when they come in contact with one or more accessible parts of an installation or an equipment. So now what we need to keep in mind is that the leakage current test is, some standards are pretty heavily involved with leakage current tests, while others are not. A good example of a test standard or requirements, that involve the leakage current test pretty heavily is the medical standard, the IEC 60601-1 3rd edition. So we're going to look at some examples from that, and just keep that standard in mind when we look through some of the medical measuring devices and some of the videos that we're going to show you. So going back to the earth leakage current, remember this is the overall current that flows through the protective conductor, earth conductor. So in other words, if you focus on this picture, we have our little medical device on the right side, and the human comes in contact with the protective earth conductor, which is the ground pin on the on a device's line cord, for example, or it could be the ground stud on the back of the device. And the human in this in this image is basically representing the MD, which is the measuring device circuit, which varies by standard. So any standard that calls out a leakage current test requirement must also specify or point to a certain measuring device circuit that needs to be used to make those leakage current measurements. So going back to the earth leakage tests, it's the overall leakage current that flows from the protective earth conductor of any device back to earth ground. And in this case, the human being is basically representing the measuring device circuit model. So once again, it's very important to be able to differentiate between the leakage current that we're talking about today for a leakage current test versus the high pot leakage current that we've been used to hearing mostly. And once again, the insulation during a high pot test, the insulation stress with high voltage leakage current is measured, and a pass-fail condition is determined based on the high and the low limits. Whereas during a leakage current test, the device is powered up during various operation states. And the high pot test basically measures the leakage through a product's insulation while the device is powered off, and insulation is stressed by high voltage, and the resulting leakage current is measured. So we looked at the earth leakage current, and the next one that I want to cover today is the touch current or the enclosure leakage current, which is another very important leakage current test specified by a number of different test standards, including an IT standard. So what happens during an enclosure leakage or a touch current test? Well, remember we looked at the earth leakage where it's the, where the human comes in contact with the protective conductor, current protective conductor of the device. And, the overall leakage current flows through the measuring device circuit or the human. For a touch current test, there's a couple of different ways, you can measure this current. It's basically, first of all, the human can come in contact with any enclosure point on the device. It could be a medical device or any other, large device that may have an enclosure, a conductive enclosure, which may, result in some leakage current flowing through it. So on the picture on the left, the human being comes in contact at one point on the enclosure, so the current flows through the human being back to the earth ground. In the picture on the right side, the person is coming in contact with two different points on the enclosure. This means that you're basically becoming a part of the circuit, because the current is going to enter you from one hand and flow through the human body and come out from the other. So in this case, the human touches two parts of the enclosure. And and it could be, again, it could be more than one enclosure point for any given device. So it's important to determine, when you're designing a product, you must know as an engineer what type of enclosure does my device incorporate, and whether it would require an enclosure leakage test or not. So let's talk a little bit about the measuring device circuit, because that's really the main the main factor that contributes, or that measures the leakage current, is the measuring device circuit. And really what a measuring device circuit does is that it simulates a human body impedance under different conditions, which is why the measuring device circuit for different standards, it varies. And we'll show you some examples of measuring device circuits, but leakage current is measured through a human body impedance network, also known as the measuring device circuit. And the measuring device circuit is designed to simulate the impedance of the human body under various conditions. Certain fault conditions are also required to be used, single fault conditions, and then you can also make the measurements in normal conditions. By fault conditions, I mean something like opening of the neutral conductor, or breaking of the neutral conductor, or reversing of the polarity. So those are considered as fault conditions. And for a leakage current test, whether it's earth leakage or touch current leakage, measurements are taken under normal conditions and also taken under single fault conditions to simulate worst case scenarios. So what's the main question here to ask is, what is the severity of electric current someone would be exposed to if they were to touch the DUT under such conditions? So in simple words, basically what we're trying to do, by performing a leakage current test, we're making sure that, when the device is powered on, it's plugged into the wall outlet or its power source. And if somebody comes in contact with the device and, at various different points, whether it's the ground conductor of the device or the chassis of the device or the enclosure of the device, what's the worst case scenario, and what's the highest current that can flow through that human being? So manufacturers of electronic products must obviously are responsible to make sure that their devices are safe to use by the end user, especially when you're a medical device manufacturer. Your devices will be used in hospitals with patients, and it just makes it just basically brings the risk level a little bit higher when when a patient in the hospital is touching some sort of electronic device. There's always a chance that something can go wrong inside the device, and the patient can be exposed to dangerous levels of leakage current. So going back to the measuring device circuits, here's a few examples. These screens, first of all, are taken out of one of our leakage current or electrical safety analyzers, the Omnia 2 model or Omnia 2 series. And these measuring device circuits are built into this device. And as you can see on the very left, we're looking at the IEC 60601 or UL 2601 measuring device circuit for the medical industry, or for the medical standard. And if you look at if you focus on the circuit, it's basically, it's two resistors and along with a capacitor. And obviously, there's a frequency weighted response for each medical device, and that's why, the readings are taken accordingly. On the right side, we're looking at the IT equipment measuring device circuit. This circuit looks a little bit more complex or complicated than compared to the MD of the medical standard. This one has a lot more resistors, capacitors, and once again, going back to the design of the measuring device circuit, it's specified by the standard. It's designed according to the type of device that's, that the human being comes in contact with. So that's why they vary in types. And then there's a very simple one we're looking at UL1563, just a resistor and a capacitor. And once again, these are just different examples of what I was saying earlier about how the measuring device circuit can vary from standard to standard. So once again, always look at the test standard to get the most accurate information regarding what type of measuring device circuit will you need to use. And also all the maximum allowable leakage current values are listed in the standards. So always references the standards when you're setting up or looking for information on how to set up the leakage current tests for your industry or for your product. So with that, we are here at our first poll question, which is, how is the leakage current measured during a leakage current test different from the leakage current measured during the high-pot test? So I know we just talked about this, so take a few minutes to attempt this poll question.
Hi, Syed. The results are in. So how is leakage current measured during a leakage current test different from the leakage current measured during the high-pot test? There were no results for line leakage always leaks from line to ground, and no results for line leakage is always purely resistive. 20% said line leakage is measured with device under test powered off, and 80% said line leakage is measured during a measuring device.
All right, thanks, Amanda. Thanks for sharing the results. Once again, thank you all for attempting this poll question. And looks like most of you had the right answer, which was D. Line leakage is measured using a measuring device circuit, and that's I guess a big difference between the high-pot test and leakage current test, along with the fact that the device under test must be powered on, not off, for a leakage current test. Okay, so let's move on and let's start looking at some of the test parameters. Once again, these screens are right out of one of our Omnia models that can do a variety of leakage current tests. And starting with the first test parameter. So now we're looking at how we're going to set up a leakage current test, whether it be an earth leakage or an enclosure leakage, and I'll tell you how the difference comes in when you're setting up the test, what differentiates a touch current from a earth leakage test. So the first parameter that we want to set up is our leakage high and low limits. These are our main failure detectors, meaning that the high limit for the leakage current would be right out of the standard, and where the standard will tell you or give you a table of values of maximum allowable leakage current values for different tests under different fault conditions and normal conditions. So this number comes directly from the standard. Leakage low, you can obviously set a low limit as well once you've determined that a certain type of product is leaking. For example, 100 microamps, you can set your low limit to 50 so that you don't have any false passes. Or if you forget to connect something, or if you didn't run the test properly, you want to make sure that you're not passing any product falsely. Then we have our voltage high and low limits, which again, obviously, remember that in a leakage current test, the device under test must be powered on. So for that, we need an AC power source, or some kind of power source to provide the power for the device under test to power up or power on. And in doing so, we're going to have to set a voltage value. So this is the high and the low limit for the voltage that will make sure that we are testing our product at the right voltage, or at least within the range specified by the test standard. And then we have our dwell time and delay times. These are just times for how long the test is going to run. And then we also have a delay time that you can always program in your leakage current test step to allow more time for your device and your test to either fully power on or settle down or stabilize before any leakage current measurement is being made. And then we have the offset parameter, which basically allows us to offset the system leakage, because sometimes, in a big test system where you have a bunch of different wires and test leads connected, maybe using some multiplexers or different connection types, can contribute to the overall leakage readings. So sometimes it's a good idea to perform an automatic offset and offset the system leakage from the final result of leakage current test that you're going to see. On the right side are what we've been talking about as the fault conditions. We have the neutral, the reverse, and the ground. You could have either neutral closed or open. Obviously, neutral closed is normal. Neutral open means you've basically broken the neutral connection. And that's followed by the reverse polarity. Basically, you can reverse the polarity or simulate a reverse polarity condition. And that's followed by a ground closed and open. And then we have our MD circuit, which you can select from a bunch of different ones that are already incorporated inside our leakage current analyzers. And then most importantly, we have the probe configuration. This is what really sets apart the leakage current, the different types of leakage current tests. Like, for example, for an earth leakage test, we will set our probe configuration to ground to line, because what we basically want to measure is the overall leakage current flowing through the measuring device circuit back to the neutral side of the line. And there's a few other circuit diagrams that I'm going to show you guys to kind of reinforce these concepts of how these fault conditions, probe settings, and MD selections are achieved inside the leakage current analyzer. Okay, and in the picture in the bottom, there's some other features of the Omnia 2 analyzer that are not important at this point. If you focus on the picture at the bottom, this is the setup for the AC source. So what we're looking at is the setup for an internal AC source of one of our leakage current analyzers, the Omnia 2 series, possibly model 8207 or 8257s, and that come built, with a built-in AC source. So obviously, remember that if you compare the voltage high and voltage low parameters that we were looking at earlier, this is where the AC source is set up to output the voltage that will be applied to the device under test. Now, if you consider the medical standard for the voltage, it basically tells you to apply or test the device at 110% of the rated voltage. So obviously, you do need a programmable AC source that can be programmed to the specific voltage value that the standard wants you to test at. And so that's the voltage value followed by the frequency. Obviously, you can test it at 60 or 50 depending on the region you're in. And then there's a current high limit, that you can always program. And there's again some other features of the AC source on the right side that we're not gonna focus much on for this webinar. And here's a basic setup for a leakage current test. And the reason I want to show you this picture is that so that we can have an idea of what all is involved when making leakage current test measurements. So what we're looking at here is a leakage current analyzer. Once again, we're showing the Omnia 2 series model here. And let's start looking at the adapter box connections first. So this is where this is where the device under test will be plugged into for a safe connection, for making leakage current measurements. So we have our, labeled 1 and 2 are our line and neutral connections for the adapter box, and the red wire labeled number 3 is the GND, the ground connection. And on the very bottom, left, we have the little sign of an AC source that's denoted by APT as well. What we're showing here is the AC source that's feeding the power for the device under test to power on. So obviously there are, if you look at different leakage current, testers, some come built, with a built-in AC power source, some don't. So in this case, we're showing one without an internal AC source, and that's why we're required to use an external AC source. And again, it has to be an adjustable AC source so that you can set the correct voltage. The other few connections that we see here are, the important ones are number 5 and 6. Those are the probe connections, the probe high and probe low. So for some special cases of leakage current tests, you are required to measure the leakage current either on the surface of the product, like the touch current or the enclosure leakage test that we talked about. In some cases, especially for a medical device, there may be requirements to test some patient connections, or in other words, what we call the applied parts, anything that basically makes a physical contact with the patient. Anything that the patient comes in contact with must be tested, because it does have some potential of leaking some current through that point, and that current can then flow through the patient. So here's basically what we consider a mini MET test system with everything that you need to make to test your product and measure different leakage current types on your product. So let's go back to our fault conditions. And as I said, most modern leakage current test analyzers are capable of simulating the fault conditions that we've talked about internally. So that means it's got the circuitry and the hardware internally to be able to simulate or induce these fault conditions for the purpose of leakage current tests. So in this case, let's look at the normal conditions first. And there's 3 switches that we're looking at: S1, S2, and followed by S3. And then we have our little MD circuit sitting at the bottom. Switch S1 basically simulates an open neutral condition. So as you can see, when I move from a normal condition to a open neutral condition, S1 opens, and this simulates leakage current measurement during an open neutral fault condition. This is one of the single fault conditions. And the other thing is, what's important to note here is the location of the MD circuit. The way I like to explain leakage current tests to anyone is that it's all about placing the measuring device circuit, or putting the measuring device circuit in the correct position or in the right spot. And that's basically achieved by those different probe conditions that we talked about, and we'll look at those in a circuit diagram shortly. So open neutral condition, obviously the device will power down because you've basically broken the neutral connection, but there still could be some leakage flowing because the neutral is sometimes grounded and the line is still there active. The next fault condition that we're looking at now is the reverse polarity. And as you can see, when I switched the slides, the switch S2, it moved in the upward position, reversing the polarity, meaning line becomes, it's just like, taking a line cord and, plugging it in a manner that line touches the neutral and neutral touches the line on the wall. So basically reversing of the polarity. That's another single fault conditions, one of the single fault conditions that's required by some standards. And again, there's going to be, the leakage current is going to change when it's being measured under a reverse polarity simulation. And lastly, we have the open ground condition. Now, this is basically not really a fault condition, because if you look at this circuit, if you focus on this diagram right now, we see that the current flows from the ground conductor into the from the device under test, and it's it's flowing through the MD at the very bottom. So if I don't open my ground conductor or switch S3, I might not get any readings because we're basically going to short out the measuring device circuit, and we're basically, or in other words, we're going to provide a different path for the leakage current to flow. So it's not going to flow through the measuring device circuit, and we may not see any leakage current. So whenever you're setting up a leakage current test, you will notice that if you leave the ground conductor open, then the leakage current will be flowing through the measuring device circuit, and you will see a value of leakage current displayed on the screen. But if you don't open the ground conductor, if you leave it closed, you're basically providing another path for that current to flow, and it's going to avoid the MD and just take the easier path back to the neutral side. So once again, the open ground is not really considered a fault condition, but you have to keep it open to actually see some sort of measurement. So that takes us to the test standards, and I know we've had some difficulty with our audio, which took up some time, but we'll try and cover whatever we can. So looking at this example of the big medical standards 60601-1, if you look at if you read through the requirements, it says tested in normal conditions and single fault conditions. So those are the fault condition that we just looked at. Tested with supply at 110% of highest rated mains voltage. This means that if you're in the U.S. and you're keeping 120 volts power in mind, 110% of that would be 132 volts. So if you're testing a medical device in the U.S. or for U.S. Market, you must test it at 132 volts of the mains voltage, and also at the correct frequency. Obviously, in the U.S., it's going to be 60. And then on the right side, if you look at the pass criteria for the earth leakage test, it says less than equal to 5 milliamps, and the NC here means normal conditions, or 10 milliamps under single fault conditions, SFC. So this is where what I was mentioning earlier, that the standard will give you a solid number to work with, or to program in your leakage current test as the maximum allowable leakage current under different fault conditions. So in this case, I would set my high limit that we looked at for leakage high to 5 milliamps or 10 milliamps if I'm using one of the fault conditions. Similarly, for touch current or the enclosure leakage test, as you can see, the allowable limit significantly reduces down to 100 microamps, less than equal to 100 microamps, or 500 microamps for a single fault condition. So once again, this would be our high limit, the leakage high limit parameter. And besides the earth leakage test or the touch current test, there's there are a few other types of leakage current tests, and that's why the leakage current, the term leakage current itself, is a very broad term, because it incorporates a bunch of different types of leakage current tests that may or may not be required based on the type of product and type of connections that product has and type of use that product has, how it's going to come in contact with people and how it's going to be connected. That all determines what types of leakage current tests will be applicable for that given device. And we will cover more of those advanced types of leakage current tests, like the patient leakage, the patient auxiliary leakage, the applied part leakage, the mains on applied part leakage, the mains on signal IO or SIPSOP, and we'll look at those different types of leakage current tests in our next webinar, which is leakage current 102. But for now, we'll focus on back to the earth leakage and the touch current leakage. Another requirement from a 61010 standard, this is the laboratory equipment, and in fact all the test and measurement equipment, the type of stuff that we make as a manufacturer of electrical safety test equipment, we have to comply with this standard and make sure that our products, before we put them in your hands are complying with the standard. And as you can see, the requirements are similar. The numbers may change a little bit, but what's important to note here is that it's the test standard is giving you all the information that you will need to set up your leakage current test and to find the right parameters, and also determine what type of leakage current tester would be suitable for your application. Another standard, the IT standard, and who would have thought that the IT equipment would require a leakage current test, but it really does. And again, it specifies its own measuring device circuit and its own maximum allowable leakage current values. And it requires an earth leakage test as well as a touch current leakage test. So as you can see, compared to medical standard, the IT standard, the 60950, only requires two different types of leakage current tests, the earth leakage and the touch current leakage. Whereas, a medical device may require a lot more different types of leakage current tests. So that brings us to a quick video demonstration. I have a little video that I made, once again, going over, we did go over a little bit of the parameters earlier, but I do want to focus a little bit more on those. Once again, the leakage high, the leakage low, the voltage, obviously the voltage high and low limits. In this case, we're assuming that we're running one of those, tests with a 5,000 microamp high limit. And it's an earth leakage test. We're setting a voltage of 132 volts, or something like that for our voltage source. So I'm going to set my voltage high to 140. I'm setting my voltage low to 128. Again, these are parameters that you can gradually adjust and kind of make a very tight high and low limit so that your product is tested strictly under those between the allowable voltage limits and the current limits. Dwell time, delay time, and here's an important one that I wanted to look at. This is again how you set the fault conditions in one of our analyzers. You can open or close the neutral switch, and then that's going to be followed by the reverse polarity condition. You can set it either to on or off, and you can see the switch that's being pointed to in the picture moving. And this is basically, once again, it's all happening inside this leakage current analyzer. So no need to do anything externally. This is all being taken care of by the hardware and the circuitry inside. And then we have the ground condition. And here's a selection of MDs that you can have, inside one of our analyzers. It's got a bunch of different measuring device circuits, and not just the ones that are listed here. A lot of different standards point to other standards for using, the type of measuring device circuit. So, this covers a pretty big variety of measuring device circuits. The next thing I want to show you is the probe configuration, and I'm just gonna rewind here real quick, because what we're looking at right now is, if you focus on the MD, on our MD on the right side of the picture, bottom right, you can see that the measuring device circuit is sitting right between the earth or the grounding conductor of our product, and the leakage current will flow through that. But the ground switch is open, and this is where I was talking about earlier. If you close this, all the current will just take this path, and nothing will be measured by the MD, because no current is going to flow through the MD. So it's important to leave the ground switch open, and the current will flow through the MD back to the neutral side. And MD is going to make the leakage current measurement. Next is the probe high-to line configuration for touch current. So this is where the difference comes in. Now, if you look at the right side, focus on the right side of the picture, the switch that says SH for so the switch high is has switched from point A to point B, which means we're going to have to use one of the probes, which is the probe high. So we're going to take the probe high and touch it or connect it to the enclosure of our product, because we're making touch current measurements. And this is how our analyzers make it possible for the users to measure touch current, is by touching the probe high on the enclosure, on the product's enclosure, and performing the test. So in this case, as you can see, the probe high touches the the point that's being tested. The current flows from probe high through the MD back to the neutral site, and it's being again measured by the MD circuit. Lastly, we have our point-to-point leakage current that could involve a applied part, or multiple patient currents, or a patient leakage test, or point-to-point leakage, in other words. And as you can see, the difference here is, if you focus again on the right side of the picture, the switch SH and SL are both on the position B. This means that now the measuring device circuit is sitting between my two probes, probe high and probe low, which means I have to use both these probes to make the measurement. If I want to measure how much current is flowing from between point A and point B, I'm going to touch one of my probes on point A and the other one on point B, and whatever current flows through between those points will flow through the measuring device circuit, and you'll see some sort of reading. So this is what kind of differentiates an earth leakage test from a touch current and a point-to-point leakage current. And like I said, in our next webinar, we will focus more on the probe high to probe low setting for point-to-point and patient leakage and applied part leakage. Okay, so once again, these were all the different probe configurations, and then we have leakage, whether you want to set it to RMS or not. And lastly, we're going to show you the AC source. Once again, like I said, it's being set to 132 volts, 110% of rated voltage, 60 hertz, and you can always set a high limit for the current draw as well. So this was the setup for a leakage current test. The next thing I'm going to show you in the video is actually performing an earth leakage test. Now, obviously, you don't see much happening, apart from the fact that you might see the light on the device under test turning on. In this image, what we're showing you is one of our leakage current analyzers on the left side of the picture, and then our small medical device that we're testing inside a safety enclosure. And the adapter box, it's basically the same setup that I showed you earlier in the picture, in a graphical image, where we had the device under test, the Omni analyzer, the adapter box, and the probes and all that. So that's basically, this is a real setup of that picture. So our device is safely plugged into the adapter box. Okay, that's where it gets the power. And we're only going to show you an earth leakage test here. So focusing on the screen of our analyzer, we have 4 different earth leakage tests set up. As we get ready to start the testing, the first step with the normal conditions. Next step, you have open ground. This time we have a reverse polarity, followed by an open neutral condition. So as you can see how the leakage current values were different for those 4 different test types. And focusing back on our device under test, we're going to run this test one more time to show you that the device actually powers on, or at least it gets the auxiliary power. And obviously, in some cases, it is required by per the standard to push the main power button on the device in the on position. But as you can see, the green LED at the bottom is turning on, which is showing us that there's power coming to this device and the circuit inside it is being energized. And again, we're looking at the earth leakage current. So remember that it's all being taken care of. We have the ground conductor here on the adapter box. We have the neutral and line. So those are all the different connections that we need in order to make the earth leakage measurements. Once again, we're running through the same steps again, and looking at the leakage current values. As you can see, under different fault conditions, the leakage current value may actually increase or decrease depending on what type of device you're testing. So that was a little video that I had for you, and now we're going to look at one of our next poll questions, which is what are some of the difficulties that you encounter when you're running a leakage current test? So we basically want to know what are your main pain points and how can we make a leakage current test easier for you guys to perform. So please take a minute to participate in this short poll.
Hi, Syed. The results are in. So what are some of the difficulties you encounter when running a leakage current test? 25% said measurement uncertainty. Nobody responded to verification of the test instrument. 25% said operator safety. 50% said making the test connections, and there were no results for other.
All right, thanks, Amanda. Thank you all for participating in this very important poll question. And once again, this was more for us to get an idea of what type of difficulties do our customers face when they're performing a leakage current test. And all of these are pretty valid points, so there's no right or wrong answer here. And that's why we left the choice E as other. Please email us with your concerns. So we would really like to hear from you how how we can make our equipment better, how we can improve on our equipment, or how we can suggest you better ways to make your leakage current test setup easier, and so you can you can be sure of that you're first of all you're not facing any measurement uncertainties. Verification of the test instrument is also very important. You want to make only an equipment that's working well will make good measurements. So it's important to verify and run some daily verification using some known loads to make sure that your leakage current tester is passing and failing as it should. Operator safety is obviously it's a very high priority for any electrical safety test area or station, and we do have some recommendations for operator safety as well. Making the test connections can become complicated depending on the number of test points that you need to test. In some cases there are a lot of different test points that you need to test, and so making all the connections using multiplexers and various other techniques to make the correct connections can be time consuming and a bit complicated. So yeah, thanks again for letting us know what your concerns are, and we'll definitely look into those, and please email us with more details if you can. So that takes us towards the very end of our webinar, and lastly I would like to show you the same picture that I showed you earlier, but only the difference here is that we're showing a computer and a software controlling our little med test system for medical device industry and for the entire compliance industry these days. We data capturing is a very important tool, and most of our customers and people in this industry that we work with are all about capturing the data, having some traceability, storing that data, and being able to show that data to auditors upon request. So it is very important to have a med test system that is reliable, easy to use, safe to use, as well as it has the capability. It allows you to automatically run control the system and execute the test and capture the data. So all the things that I've talked about, a lot more details are available for you to look at or view on our, as our educational resources on our website, on arisafety.com, on support, educational resources. Feel free to look through or browse through our website, and if you find any material useful, feel free to read it, download it, and read it. And if you have any questions, reach out to us, and we'll be happy to assist you or answer any questions that you may have. Our next webinar, which is will basically be a continuation of this webinar, is Leakage Current 102. We will be covering the more advanced types of leakage current tests, like patient leakage, applied part leakage. So do join us on Wednesday, November 7th at 10 a.m. and we will make sure that we finish the topic of leakage current tests, and that would be our last webinar of the year as well. So once again, I'm going to leave some time open for any questions that you may have on the chat line that I can answer for all of you. If not, I appreciate you guys taking out time to join us today on Halloween Day, and happy Halloween to all of you, and we'll see you next time. This is your host, presenter Syed, and along with the rest of our team. Thank you, and we're now open for any questions.
Sad, I don't see any questions listed right now, but if anybody has any questions, obviously they could email us or email Amanda, and we'll definitely get back to you. Okay,
thanks, Vishan. So it looks like we don't have any questions on the chat line for everyone to, for me to answer for everyone. So we're going to end our webinar here. Once again, thank you for joining us. We'll see you next time.